Today's lecture is a good one, folks. It's Ampere's law. Which is like the Gauss's law of magnetic fields. You can use it to find the magnetic field in problems that have lots of symmetry from the current. It's amazing. Let me start by telling you what it is. All right, so actual, like the full version of Ampere's law looks like this. The line integral of the magnetic field around a closed path is equal to the current flowing through the surface that is defined by that path. Right, so if this is the surface, this is the boundary of the surface, plus the time derivative of the electric flux. Now, this is the only time I'm going to talk about it in this form today because we are assuming that nothing is time varying here, so we're just going to take away this term and only talk about this. When it doesn't have that time varying term, this version is called Ampere's circuital law. And that's what we can use to find the magnetic field here from a current distribution over here. In general, it can be used in situations that have a lot of symmetry, very much like Gauss's law. If your problem is not super simple and you can't define a nice boundary around which to do this closed path integral, you're back to using Biot-Savart law. To illustrate this, let's do a really simple example. We can verify it using the infinite wire. So let's say we have an infinitely long wire and it is carrying a current I. And let's define this as the z direction. We're in cylindrical coordinates, so I'll draw your x and y axes. But just remember that phi is determined going right-hand rule-wise around the z-axis, starting at the x-axis for 0. All right, so you can choose any loop that this wire passes through, right, for our Ampere's law. Any loop will do, but in order to really apply it in a useful way, we would like to choose a loop that satisfies a lot of symmetry conditions so that we'll actually be able to solve for an unknown h, even though we already know what h is for this problem. We're going to pretend we don't know it in terms of the current. So what we're going to do is we're going to say symmetry-wise, we could shift this problem along z and nothing would happen. So h doesn't depend on z. Similarly, we could rotate this problem around by changing where the 0 value of phi is. Nothing would happen. So it doesn't depend on phi either. But if we moved the wire in radius, or if we moved ourselves away from the wire in radius, we would expect something different to happen. So it does depend on rho. That's step one. Figure out which variables it depends on and doesn't depend on. We also expect that h will only have a phi component in vector direction. With that in mind, we would like to choose a path for our Ampere's law application that is a path of constant rho and that moves along phi. otherwise known as a circle. We're going to choose a circle of radius rho, and we're going to allow that value of rho to be a variable so that we can find the value of the magnetic field everywhere in space. Now this flux integral of current dot ds. Our current here is a line current I, so that just evaluates over the surface of the circle to be I. Easy peasy. Sometimes you will have a current density that actually depends on position, and when it does, you'll have to actually evaluate this integral. Next, we need to evaluate this path integral. So, out of these steps 1 and 2, we know that h has this form. Some amplitude, which is a function of rho, times a hat phi. And what we're trying to do here is solve for what function of rho is this? Okay. H dot dl is actually going to be the integral from phi equals 0 to 2 pi. Substitute in my value of h here, so amplitude of h, which is a function of rho, times a hat phi, dotted with dl, and dl around the edge of a circle is a hat phi rho d phi. And that whole thing is equal to I. I'll try to fit that on the screen. There we go. How do I evaluate this? This dot product evaluates to 1. Our integral is being done with respect to phi. Everything else in here depends on rho. So none of that stuff is really affected by it. We just get the integral from 0 to 2 pi of d phi, which gets us a factor of 2 pi. So the result here is that h of rho times 2 pi. Whoops. There you go. H of rho times 2 pi is equal to the current. So h of rho is I over 2 pi rho. Cool. Which means that our final magnetic field expression is going to be a hat phi I over 2 pi rho. This is a pretty basic example of how you can apply Ampere's law to find the magnetic field due to a current distribution that has a lot of symmetry. So just to really lay out explicitly what we have done in practice here, I'm going to tell you what are the requirements for choosing your Amperian path. All right, so we're choosing this closed path, which is the rules for it are very similar to the rules for choosing your Gaussian surface when you're applying Gauss's law, but obviously it's a closed path rather than a closed surface. So here are the rules. 1, we need the magnetic field parallel to dl, or magnetic field perpendicular to dl, or magnetic field equals 0 on the path. One of these things must be true everywhere on the path. Requirement number 2, we need the magnitude of the magnetic field constant along the path. Otherwise, when we try to do the integral along the path, we will be integrating an unknown variable that is changing, so we won't be able to extract the magnitude of the magnetic field out of that integral, which is the entire point of doing the integral in the first place. So this one really needs to be true, otherwise we can't do it. Last thing is that you need to be able to find the solution to the current integral. So the total current passing through the surface whose boundary is the path. And that one should be pretty simple. And if you find that you have satisfied the first two conditions and there is no current passing through the surface, guess what? Your magnetic field is 0. Ta-da!